Yeah, we have a pleasure of hosting Akhil Prem Kumar. He recently made transition from like physics research to machine learning research, and he's been focusing on intersection of information theory and machine learning. Yeah, with that, I would like to hand it over to Akhil, and who will give us more details about it.
All right. Thanks, Diane. I hope I'm saying that right. Thanks for the invitation. So let me just jump directly into the talk. So hopefully everyone can see my screen.
Yep.
Oops. All right. So, I'm just going to broadly speak about some connections I've noticed between information theory and machine learning, and specifically generative modeling. And I'm going to mostly concentrate on diffusion models. So this talk was designed for a very broad audience, so it's not super mathematical. My hope is that I can just convey the intuition behind the actual mathematics. So I'll mostly just use diagrams and animations.
Yeah. I would say that the audience is broad here as well, because there are some people that study physics, but some people that are mostly doing machine learning or language modeling. So that
okay,
I think it's a good example.
All right, sounds good. Have any of you seen any of my talks before?
No, I mean at least I didn't.
All right, good.
I think we have seen the one on the entropy diffusion.
I've also seen the one on neural entropy.
Okay, so the first half is basically exactly the same as that, but I'll kind of delve into some of the more recent stuff as we go on. All right. So let me see. Yeah. So if you take like a bird's eye view of the current state of generative AI, you'll see that there are these like two pillars to a rough approximation, which is LLMs and diffusion models. And if you've been kind of staying current with your generative modeling news, then you'll have noticed things like Gemini diffusion, which are diffusion language models. So maybe these two pillars aren't actually quite separate. Maybe they kind of have some overlap. But we also know diffusion as something that appears very frequently in physics and chemistry and basically all of the sciences. And in physics, you can kind of place it under the umbrella of thermodynamics and statistical mechanics. Now, the thing about thermodynamics is that it is kind of the original effective theory, because you're essentially doing effective theory, but you're integrating out all the degrees of freedom to its very extreme to get just a handful of numbers. Thermodynamics is also just an instantiation of information theory. So it's information theory applied to physical systems. So the broad theme of my research right now is to see if we can use this connection between diffusion and information theory to import some information theoretic ideas into machine learning. Okay, so I'll jump directly into the generative modeling problem, which I'm sure all of you are familiar with, but I'll kind of quickly review anyway. So suppose you have some data distribution which you don't know, but you have access to this distribution through its samples. So you have some training data, which, for diffusion models, it could be some images or videos, right? And importantly, there's only a finite number of these samples, and these samples live in, a super high dimensional space. And therefore, the data is both finite and very sparse. Now, in this scenario, you have the following problem, which is that there are many distributions that could have produced the exact same set of samples, right? In fact, each of these candidate distributions have their own probability of having produced these samples. So there is a distribution of distributions. So the picture on the right here is, I basically converted all of the candidate distributions to a point on the x-axis, and what you're seeing here is the probability that a given candidate distribution is the true distribution, or is the distribution that produced the given samples x1 to xn. Okay. I'm going to show this in a slightly from a slightly different angle. So what I'm going to do here is I'm going to place a bunch of I'm going to show you how the distribution of distributions and the candidate distributions evolve if you have more and more data samples. So I want you to pay attention to the these points here. By the way, can you see my cursor? Okay, so I place more and more samples, and you see how the candidate distributions kind of all start coalescing onto one another, right? And this should already remind you of what happens in equilibrium statistical mechanics. So the mental map you should make is that the candidate distributions are like the microstates. And if you have some large n, which for a system which is like a gas in a container or something, n is the number of particles, and here n is the number of samples. So if you have a large n, then by the law of large numbers or the asymptotic equipartition principle, whichever you want to use, you find that all of the microstates, all of the most probable microstates are kind of going to fall roughly near each other in this way, right? Now, there is one more missing piece here, and to identify that, I'm going to write down an expression for the distribution of distributions in terms of the using Bayes' theorem. And so I write down this expression, and I have to now account for this prior here, which I'll kind of show with this brown line here. So the prior here is just a pool of candidate distributions from which we draw our, these colored lines here, which are the candidates. And for example, if you want to choose a prior which only has, sufficiently smooth distributions, then you're basically restricting yourself to candidate distributions that have that property, right? Now, the first term here, the likelihood, can actually be simplified by noting that it just factorizes into a product of probabilities evaluated on the particular chosen candidate distribution, right? And our goal is to find that one particular candidate which is most probable given the data. And so that means maximizing the right-hand side here. And if you assume that the prior is sufficiently flat, then in the leading sense, you basically get the maximum likelihood condition, right? So again, this is basically a cartoon of what happens, and there are actually some important effects that you have to account for when the prior isn't this flat, but I'm assuming that the prior is like really flat around this peak. Okay. Now, in machine learning, you kind of choose a model with some parameters theta, and these theta parameterize your candidate distributions. And therefore, you kind of have the equivalent expression, which I've shown on the right here. And it's important to choose a model or a set of prior or a prior over the parameters, which actually contains your true model within it, right? So a simple example is this could be like a Gaussian mixture model, in which case the theta are just the mu's and sigmas of the Gaussian mixture and the component probabilities, right? All right. So we already kind of hinted at this connection to statistical mechanics, and I talked about how the candidate distributions are like microstates. And there is this picture we often see in graduate textbooks on statistical mechanics about how the microstates are basically just states occupied by a large ensemble of identically prepared systems, right? And so I'll kind of use the same picture here, except I'm going to choose a very specific kind of system, which is a diffusing system. And what I've shown here is just some ink particles in red, which are diffusing in a bath of water, right? So let's say I initialize all of these uh, diffusing systems with the same initial state somehow. And you have to also imagine that there is like a very large number of these, not just 6. So I start from the same state and I let each of these systems evolve under their diffusive dynamics. And if you wait for some time, you find that these ink particles kind of, get kicked around by Brownian noise and equilibrate to fill up the space available to them, right? But if you wait for a little longer, you will find that some systems actually deviate a little bit from the equilibrium configuration. So I've drawn a very exaggerated version of that happening here. So one of these systems has actually ended up in some exotic state, which is not the equilibrium state of the native diffusion equation for this system. Which also means that this is a highly improbable event, right? So if I were to call each of these equilibrium distributions P equilibrium, and let me call the exotic state P star, which by the way, I have just taken the densities of the red particles and normalized them to interpret them as a probability. So, density and probability kind of roughly mean the same thing here. All right. So if I do this, then what I can see is that the distribution of all of the outcomes kind of has roughly this shape for a large number of diffusing particles or ink particles. And you see that P equilibrium is kind of the dominant outcome that you would expect from this experiment. But there are some other exotic states which are extremely improbable, but still are admissible. All right. So the question here is, can you somehow modify the diffusion dynamics, let's say by introducing some sort of external field or perturbation of some sort, so that P star becomes the dominant outcome? Okay. And this problem has basically the same structure as the one that we were just looking at from the when we were discussing like the Bayesian picture. So what I would do is I would first need to specify what P star is by specifying the location of each of those ink particles. And then I write down an equation that looks like this. So what I have written here is the distribution over the different outcomes is basically my posterior, right? And the symbol U here is just denoting a different diffusion processes. So PU is some sort of a pool of different diffusion processes. Let's say they differ by their drift term or something. And I want to pick from this pool a particular diffusion process which maximizes this sum over log PU evaluated at the target points. Okay. Any questions so far? All right. So the whole question is, how do we then choose this U, right? Because if you knew how to do that, then we can apply it to any P star. And in particular, I can apply it to the case where P star is the data distribution that I want. So I want to find a diffusion process that guarantees that PD is the outcome. All right. And to find a way to do this, we turn to this thought experiment by Schrodinger. So Schrodinger basically asked the following question. Suppose you have a diffusing system, and in this case, I'm going to assume that the initial configuration of my system is PD, which is my data distribution. And suppose I let the system equilibrate for some time, okay? So the ink particles get distributed evenly, and at the end of this process, it's just like a homogeneous distribution. So Schrodinger asked the following question: if we wait for some finite time, what is the probability that the system basically goes back to its original configuration? In other words, what is the probability of reversal? Okay. Now, this might seem kind of like an absurd question at first because we don't see things undissolve themselves in our day-to-day life. But that does not mean it's impossible. It's just that such an event is highly improbable because of the second law of thermodynamics, right? So, in fact, if this is Brownian motion, then you also know that there are actually many ways of going back to the original configuration. So you have a situation like this where you get like a spontaneous kick on all of the ink particles and they reconfigure themselves back in the shape of PD. Or you can have a situation like this where they get many number of small kicks, which all conspire together to bring them back to PD, right? So the central kind of point that Schrodinger is trying to make can be distilled into the following binary question, which is which one of these is more likely, right? And I'm assuming you guys know the answer because you've seen the talk or the one on YouTube. Do you guys remember the answer?
The
Do you know
gradual
what?
one.
What's that?
The gradual one?
one.
Yeah.
Yeah. So the gradual one is the one that's more likely. And the simple way to understand this is to just look at like at a one-dimensional version of the problem, where if you have like a rapid jump, then it kind of looks like this. So this is a Gaussian random walker, which is supposed to just hover around the point 0, but the walker has made this extremely unlikely transition. And the second case shows also an unlikely transition, where the walker kind of keeps making a consistent choice to go in one particular direction, right? And both of these are unlikely, but one of these is more likely than the other. And you can just see that by doing the following calculation. So, if L is the size of the gap or the jump, then the first guy made the jump in a small time delta t. So the probability is e to the power minus L squared over delta t. And the second walker basically made a bunch of tiny jumps. And if you work it out, since it took this walker uppercase t time to do all these jumps, then you find that the probability that the second walker ends up at L is e to the power minus L squared or uppercase t. And since uppercase t is larger than delta t, the exponent is closer to 0, and therefore that probability is higher. And so the same story holds for the experiment with the beaker, with the ink. And in fact, what Schrodinger shows is that the most dominant way of reversal is just a playback of the forward process. So this is a nice this is super interesting from a physics perspective, because what you do in Brownian motion is that you kind of introduce this Wiener term, right? So when you write down the stochastic differential equation, you insert this Wiener term, which kind of breaks the time reversal symmetry of the problem. So if you had something which was dx equals time, something like fx times dt, then you can just reverse it by changing the sign, right? But when you introduce Brownian motion, you're kind of introducing randomness, which is what breaks time reversal symmetry. But you see that despite your attempt at breaking time reversal symmetry, the reversed dynamics still has a privileged position, which is that it remains the dominant way of going back to the original state. So we can kind of see this more pictorially by doing the following. So I'll introduce a little bit of notation. Like I said, the data distribution is just the one that corresponds to the initial ink configuration, and the equilibrium distribution is the final diffuse state. So I'll write down a stochastic differential equation, basically the simplest one I can do here, where sigma is the strength of the Wiener term. And I will denote the forward transition kernel by F. So the forward transition kernel, when applied to P equilibrium, just stays at P equilibrium, or keeps it at P equilibrium, because P equilibrium is the stationary point of F. And for the reverse dynamics, I will use a different SDE to describe it, but it is designed so that it kind of evolves the red points in exactly the same way that the forward in exactly the same way that the distribution evolved in the forward direction, but it looks like a playback. So the reverse trajectories the reverse process has a transition kernel that corresponds to R, which means that R, when applied to P equilibrium, brings you back to the data distribution, which is this. So Schrodinger's result is the following, which is that the probability of getting PD from P equilibrium, or the probability that the system automatically fluctuates from P equilibrium back to PD, has this asymptotic form, right? And you can understand this a little bit better by first, by the way, I'll draw a picture, but let me just point out that the scale is the scale between the reverse and forward kernels. I will give a better explanation of this in a minute, but I want to show you a pictographic representation of the right-hand side of the boxed equation. So let us take a plane T, which is all the processes that start at P equilibrium and take you to any other random distribution. Okay, so I'm going to plot the right-hand side, which is that exponent, over this T-plane. So you see that F is special because the KL is a non-negative convex function. So the KL is smallest at F, and therefore the forward process is the most probable, or it's where the peak of this exponential lies, right? So, which is a different way of saying that the system would like to stay at P equilibrium. So for example, the exotic evolution that we talked about earlier could be some other point on the T plane with some special process T star that takes you from the equilibrium distribution to that P star. So this picture that I'm showing you is just a slightly fancier version of the picture in 2D that I showed you earlier. But I'm not interested in going back to P star. I want to go back to the original data distribution itself, PD, right? So what I'm going to do here is on this T plane, I'm going to indicate the locus of all processes that take you back to PD. Because remember, I said that there are many ways of going back to PD. So there are many points on the T plane that would take you back to PD. And this is what it looks like. So R is basically the process of all the processes that take you back to PD, which is most probable, right? So you can imagine that R is the playback process, but the spontaneous recovery process where you get like a instantaneous kick and go back to PD, that could be a process that lives here, which is and the fact that it lives here comes from the fact that it's extremely improbable. Okay. And this is what I meant by the reverse process having a sort of or the time reverse process having a sort of privileged position. It is, out of all the processes that take you back to PD, it is the one that dominates or is the most probable, right? So this, in the asymptotic limit of large n, this the expression for PD basically is dominated by this process. And the scale is basically the gap between F and R. Okay. And at this point, I can make one more important point, which is I can talk about what happens if I choose a different forward process. So remember, we have this intuition now that if you a more gradual reversal is actually more probable, right? And we also know that the reverse process that looks like a playback of the forward process is the one that dominates. So what if we slow down the reverse process by actually slowing down the forward process itself? That is, I'm going to choose a diffusion process for which the diffusion strength is lower, which means that the forward process itself is more gradual. And since its reversal is just a playback, the reversal will also become more gradual. And what that means is if I modify my forward and reverse SDs in this way with this new reduced diffusion strength, then I find that my F and R processors are brought closer together, right? And this means that a more gradual diffusion process is more likely to automatically reverse. Although, again, we don't see this in real life because of the large N. Yes.
Could you explain to me what is the meaning of TKL divergence? So is it TKL divergence between the stochastic processes or it's a marginal?
Yeah, I'm going to explain that in literally the
Okay.
next slide. Right. Any other questions? Yeah, but for now, you can kind of use this picture of, it's kind of some sort of gap between the forward and reverse processes. And
So
in fact,
in this, you mean that the base process is fixed and essentially you either start with the beginning at end and then you either run it forward or in reverse time.
when you say base process, are you talking about the forward process?
This is a bridge situation, right? So what?
Yeah, this is the entropy regularized Schrodinger bridge, kind of. Yeah, which I'll talk about in a moment.
Okay, well, then
all right. Yeah. I also want to point out one more thing, which is that so this is the expression, asymptotic expression for the probability of getting PD starting from P equilibrium completely by random fluctuation, right? We are not going to assist the system in any way to go back to PD.
Yeah.
And you also know that minus log of a probability is an entropy, right? So if you take the minus log of this, you basically get what is called the total entropy. Of course, you have to normalize by n. So I will explain what total entropy means in a second, but let me first switch over to a slightly different picture. So I'm going to leave this picture of the ink diffusing and move on to this picture where I represent my P equilibrium on the left by some sort of simple Gaussian, and my data distribution, which you have to imagine is some extremely non-trivial distribution, is shown on the right by this bimodal thing. Now, I'm going to introduce a forward process which now has a confining drift term, because that will allow me to get rid of the beaker and still get a stationary distribution that is confined. So if I apply the forward process to PD, then it just transforms it into this generic Gaussian, which is the equilibrium state for this blue forward process. All right. And what I'm going to do here is I will apply the forward process on P equilibrium in this direction. And of course, nothing is going to happen to P equilibrium because it's already at the stationary point of the forward process. But I'm also going to apply the reverse process And I'm going to show you the difference in the shape of the envelope or the shape of the distribution if you subject the equilibrium process to both of these things. So this is basically the story of the two beakers. So you see that nothing happens to the blue curve, but the orange curve, which is the result of the reverse process, slowly changes shape and goes back to looking like PD, right? And now you get a better sense of what the KL divergence is. It is basically the KL divergence between the path measures of the reverse and forward processes. So the path measure is just a fancy word for a probability distribution over the paths. So the KL is just the KL between the probability distribution of the orange paths versus the distribution of the blue paths.
Pathwise. So it will
Yeah.
be it's the norm of the difference between the drift functions.
Yeah. That will appear. Yes, exactly.
So it divided, assuming that they have the same volatility function.
Yeah, exactly. Yeah.
Okay.
So
yeah. So in the generic bridge situation, you will, because this is a special case, right? In which one of the side is the terminal or like a asymptotic distribution of the other, the thermal equilibrium. But of course, it doesn't need the case, right? But the formula is still true in the general case, right?
Yeah. In the general case, yeah, I think you can go from any distribution to any other
Yeah.
distribution, and then all that is true. This is in the diffusion case, you choose some sort of Ornstein-Uhlenbeck process because those have an analytic expression for the finite time transition kernel, which is something you need when you want to train the model efficiently without doing explicit simulations.
Yeah, and fundamentally, we know what the stationary distribution is, right?
Yeah.
You can always do diffusion training if you to target an arbitrary distribution, but usually it's quite non-trivial to write up a process that targets an arbitrary distribution. So that's then in Schrodinger bridge, you need to train back and forth. And forth essentially. So you need to kind of train two vector fields.
Right. I think people call it iterative proportional fitting or something. So this kind of you have to go backward and forward and kind of converge on the bridge. But if you make the choice of, if you restrict yourself to these Ornstein-Uhlenbeck processes, which is the variance preserving process, right? It helps you kind of circumvent all that because you don't need to actually simulate the full trajectory. I'll come to that.
Yeah, but
but I'll come to that in a second. This is part of the talk.
Can I ask a question?
Yes, please.
From this perspective, is there a way that we can understand so because you're saying that the probability of distributions, so and you mentioned that this can be applied for any, to choose what diffusion process. So I was wondering because, I mean, from the practical perspective of diffusion models, you can have, like the variance preserving, variance exploring, and you can have all different types of functions for the drift and the diffusion term. So is there a way to kind of like make sense of what is the most probable in terms of what is the most useful choice of this diffusion on drift terms?
That's a great question. That's a great question. So in the paper, so if you look at the paper, a version of the paper that is at NeurIPS now, so I basically rewrote the entire paper from its first version. So the version in NeurIPS actually has many more experiments and addresses exactly this problem. So we try out not just the VP process, but a couple of other processes which are different from VP, and we kind of study their entropy production. And we see that VP kind of has like the lowest entropy production in the usual cases that we apply diffusion models to. But I'll talk briefly about this later in the talk.
All right, thanks.
All right. Any other questions? Okay, so moving on, let me try to figure out where I was. But so the scale is just the scale between these path measures, and the story of comparing path measures and that being the total entropy is known in thermodynamics literature as the Jarzynski equality. Although I would argue that it's basically just a version of Schrodinger's argument from 1931. Again, it is also possible to show that up to some terms that are constant or vanish in the late time limit, that the scale between path measures is also the scale between the terminal distributions. So PD, which is the result of evolving back with the reverse equation, and P equilibrium, which is the result of evolving back with just F itself. Okay, so this particular form of the Jarzynski relation can be found in this paper by
Sorry, I didn't get it. So on one side we have the pathwise scale divergence, and you're saying that that's up to constant term. It's equal to the marginal.
Exactly.
Where? At what point?
Marginal
at the final
surface. Yeah. Exactly.
So, but why is that point special? Under this special case, let's say if we had two different boundaries, then we will have some other terms, I guess.
Two different boundaries in the sense
of... because in the other boundary taken side, we have A and B, right?
Oh, yeah. So if you... So, yeah, that's right. So this is... are you talking about this boundary here?
Yeah.
Yeah, so this is... so there is some... I've suppressed some time parameters just to kind of simplify the notation, but essentially what you're... So S dot is a function of time. You can think of it in that way. So you can think of S dot as being evaluated at this time surface T, which is why it's it corresponds to this KL between the marginals at that time surface.
Oh, the margin of the time step. Okay, assuming an initial condition. Okay.
Yeah.
Makes sense.
Yeah. So there are some subtleties to this which I think you're picking up on, and those are discussed in detail in the paper. But this statement is true, and it's also in this paper. It's under the assumptions of okay, there's some contribution from the mismatch here which vanishes and so forth.
So maybe Diane, we were at some point when thinking about optimization of time point, we were thinking about the difference exactly between this pathwise KL and the marginal one. And we were of the belief that it's not equivalent to maximize. If you maximize one, you would not end up. Here you are saying that under some condition it will be equivalent.
Yes. So in the score matching parameterization, they are not equivalent. So this is quite important. So you have to go to something called entropy matching, which I don't think I have a slide which talks about it in this version of the talk, but there is a little trick you need to do to get both of them to agree. And it's a very simple reparameterization of the reverse process.
Okay. If there will be some extra terms otherwise.
Well, I don't even, yeah, okay, let's call it an extra term. There will be like an extra term in the drift. I'm happy to discuss this like later during the discussion, but that's like a little technical detail in the paper. Okay, great. Thanks for the questions. All right. So as Luca pointed out earlier, you can express the scale, the pathwise scale, as this difference between the drift terms of the forward and reverse processes, which basically gives you this expression, right? So to kind of summarize everything we've discussed so far, the reverse process knows about the PD to P equilibrium transformation because it's just a playback of that process. And this information this information is kind of captured by this score matching term, or sorry, the score term, which is this grad log P. And I put a little arrow to the left here to indicate that this score is evaluated on the forward process. And basically what the reverse process is doing is it's kind of injecting information that was eroded away in the forward process to convert P equilibrium back to PD. Right, so it's like a thermodynamic cycle. All right, now I'm going to move away from talking about the physics of diffusion to some actual ML stuff. So p-equilibrium now just means some sort of Gaussian noise distribution of, let's say, images. And if I have a way to convert p-equilibrium back to PD, then I can use that to convert this noise vector into some sort of sensible image, right? Of course, the problem still remains that we don't know what PD is. We only have access to PD through its samples. So we need to figure out what the target distribution is. And the way you do this is since we have access to these samples, we can do forward simulations of the process by just running the forward SDE on the samples themselves. So for example, I take a single point from PD and I subject it to the forward SDE, which is extremely cheap to simulate on a computer. And I can jump to some random time in the forward direction, which, by the way, this is why it's important to choose either the VE or VP process, because you can jump to this arbitrary point in time without having to do a step-by-step simulation of the entire forward process, right? Which is not true in the generic case of a Schrodinger bridge. So in that case, you kind of end up having to do like the actual step-by-step process, which is extremely expensive. All right, so I can repeat this for each sample in my training data, and that kind of starts to give me a sense of what the distribution should look like at all the intermediate times, right? Or in other words, it's basically giving me a sense of where the forward particles will be, which is also where the reversed trajectories ought to go, right? Because reversal is just a playback. So what I've shown here is just one training epoch because I've evolved all of the data samples just once. I can, of course, repeat this many times for each data sample, noising them to different arbitrary points of time. And I can have a neural network basically monitor the situation. And if I do that, basically the neural network kind of learns like I said, where the particles ought to be in the reverse process. And this structure that appears here, this kind of like blue, sidewise Y shape that appears here, that is the Schrodinger bridge. So it is this way of going from the forward, the data distribution to p-equilibrium, or equivalently from p-equilibrium back to PD. Because if we do enough of these simulations, we can kind of discover these quote unquote channels that go in either direction because they're just playbacks of one another, right? This is, of course, like a qualitative description of what happens. More practically, what you would do is you would take the neural network and you would parameterize the supposed reverse process in the following way. So you call it, I'm going to call the drift term U theta, and U theta is basically the forward drift term plus some parameterized control. Okay, so this is what's called the entropy matching model. If you use score matching, then you would say that U theta equals minus BF plus sigma squared S theta. Again, happy to talk about it later. But this is why the entropy matching parameterization is important. So if you look at the KL between the reverse and controlled processes now, it has the following expression. And it basically upper bounds the KL over the marginals. So the marginals over the data distribution as well as the reconstructed distribution, which is P theta. Now, look at what happens. And by the way, this is the training loss for a diffusion model. And of course, you kind of do some more manipulations like variance dropping and so forth. But look at what happens if I disconnect the neural network. So if the neural network is not involved in this picture, then basically I set E theta to 0. And this just becomes the difference of BR minus BR and BF. right? And if BR minus BF appears here, then the scale is just the total entropy. Or in other words, with the network disconnected, my U theta basically is the same as F. And the gap between this U theta and R is the same as the gap between F and R, which is the total entropy, right? And the process of training is basically this. The network is traveling from something that looks like the forward process to something that looks like R. So it's kind of covering this gap, which means that it's absorbing this S dot worth of information. And this is what I call neural entropy. So neural entropy is basically all of the information that the network retains, which in the ideal limit is exactly the information that you need to reinstate to go back to PD along R. Okay. Now, I also mentioned this difference between. Oh, sorry.
I have a question about it.
Yes.
Because you say like, I mean, the way we do training is like we already have a neural network with like random parameters, right? So anyways, like even if our PD is equal to P equilibrium, neural network needs to learn something, right?
Yes,
Like
in the score matching case.
Okay, so you're saying
In the
that.
score matching case. In the entropy matching case, it doesn't have to. And that's the whole point of that kind of parameterization.
I mean, but it really depends how you initialize neural network, right? Like even in an entropy matching case, like if you initialize it at random, like you would need to see data in order to understand that, like, oh, I didn't need to do anything, right? Or
Yeah. So I think that's a separate question from the first question you asked. So the first question was about, if P equilibrium and PD are the same, then does your network have to learn something, right? So in the score matching case, it will have to learn something even in the trained state. In the equilibrium, in the entropy matching case, the network basically learns that all the parameters are 0.
but it still needs to learn, right? Like, and the process of learning is like absorbing information, right?
Yeah, okay, yeah, correct. So I'm making the distinction between going from like a randomly initialized state to the final learn state. I'm just talking about like the final learn state. So how much information is stored in the final trained network? I'm not talking about what happened from the initial random weight configuration to this.
Yeah. No, I mean, why I'm asking this, like, because we're trying to understand, like, how, like, for training, which time points are important, right? And like,
Yeah,
at which time points your neural network learns the most, like, absorbs the most information.
Right. But that time is the diffusion time, right?
Yeah.
Not the training time. So there is the training epochs, which is a different time axis compared to the time axis of the diffusion process. So your question is about which point along the diffusion process is the maximum amount of information being transferred to the network.
Yeah.
Yeah. So I think I think the entropy approach can, probably used to gain some insight into that, although I have not thought about it a lot.
Okay.
But yeah, would be happy to discuss at the end of the talk.
Yeah.
Raya, you had a question, or Gabriel?
Gabriel, yeah. Quick question. Maybe you get this question a lot, but it seems to me that this entropy matching is kind of similar to flow matching, right? Because you're trying to match the velocity field.
It is the same. Yeah. It is the same loss as score matching up to some prefactors, but yeah.
I mean, flow matching, when you try to learn the drift completely instead of the score network.
Yeah, so the difference between score matching and entropy matching is just like some factor of minus x. So you add and minus x is just the drift for a VB process. So
and what you're saying is that this parameterization allows you to capture all the information, while the score matching loss, there's a gap of.
The point I'm making is I have some slides. I think maybe also here. So, okay, let me see if I can go to, let me just jump to those slides. Oh no, okay. I don't have the slides here. I had those slides in an earlier version of the talk on YouTube. But okay, let me just reshare this again.
I just wanted to try to understand if like the benefit
Yeah,
of
of
using
course.
this is
Yeah,
about from the score matching loss. So here you are making maybe the claim that you can absorb all information, right? Compared to score matching.
it's both score matching and entropy matching absorbs all of the information you need to go from one to the other. The problem is that score matching also absorbs some additional information because it has to fight this minus x term. So in the entropy matching case, it allows you to say that the network is remembering only the information relevant to going back to PD. Whereas in the score matching case, as Dion pointed out, you also have, even in the case where P equilibrium and PD are exactly the same thing, the network still has to remember some information.
I mean, the fact that we often work with EDM invariance exploding and then they're identical.
Sorry, what was that?
We often
in the
work
variance
with
exploding. Okay.
Invariance exploding case EDM, they're identical. It's the same loss.
Yeah,
okay.
Yeah, because there is no drift term.
Yeah. So it's also applied, that it means that your formula should also apply directly.
There is actually a subtle challenge there because the variance exploding process does not have a corresponding equilibrium state.
Yeah, but it usually is not that bad, right? Because it's still asymptotically up to, if you rescale it, you will get an equilibrium state. So it's does it actually create much problems? Because essentially, yeah, the variance keep increasing. That's true, but essentially it still reaches the target distribution up to rescaling.
So the point is not about reaching some target distribution. So yes, you can assume that the target distribution is some sort of uniform distribution, right? The point is when you want to take the KL at the terminal time, there is no peak, there is no denominator in the KL because there is no equilibrium distribution corresponding to a driftless diffusion process. Because you need the drift and diffusion terms to kind of work against each other and come to some sort of like and negotiate the equilibrium state. And
but does it need do you need to take it with respect of the terminal time, or can you take it with respect of an intermediate time? Because it would be with a very good approximation. If you just get, I don't know, in EDM you take t equal to 10. Yes, it's not the terminal state, but from all intended purposes it is, and you know what the distribution is.
Right. Yeah, some of the so you do lose that equality and there are some issues, basically some measure theory issues if you try to do this. I talk about this in my paper, but because of the fact that these ML conference papers have like a 9-page limit, most of these details are in the appendix. Yeah. Again, happy to talk about it more later. All right, so let me just quickly go through the rest of the talk. So I mentioned that depending on the strength of the noise, you have different forward processes, and corresponding to different forward processes, you get different amounts of entropy production, which is basically the gap between the forward and reverse processes. And that means something like this is possible, where you have some sort of privileged forward process for which the entropy production is as small as possible, right? Given that you only have like a specific amount of time to convert the transformation from PD to P equilibrium. So this lower bound is actually related to the L2 Wasserstein distance between the data distributions and the equilibrium distributions, which is extremely satisfying because it kind of neatly connects this discussion to optimal transport. And this relation is very well known in stochastic thermodynamics literature. It's called thermodynamic uncertainty because sigma squared S dot has the dimensions of energy. It's actually a free energy difference. And you know that energy times time greater than some constant is famously something that appears in quantum mechanics as the Heisenberg uncertainty principle. So there is this kind of like, is there a question?
Yeah.
Yeah.
Just to check, the thing on the left is work in stochastic thermodynamics, right?
Is what? Is what in stochastic?
Could we consider it as work, like work?
No, it's okay. So yes, you can call it. There is literature where they call it like delta W, and yes, you can call it like I forget what. It's some sort of work. Yes.
Oh yeah, because I thought like I saw it somewhere. Yeah.
Yeah, it's essentially a difference of free energy. Okay. So again, the kind of.
So, but maybe wait a second. Can we unpack the formula a moment because this sounds very important to me. So S dot is the. So what was the definition? Is the total?
Yeah, start is this
entropy.
gap, the purple line, on the left here. So
because now it's covered by Heisenberg. So can we?
Sorry. The point I was making is just the following, which is that if you are extremely aggressive in your forward diffusion process, you will generate a large amount of S dot, right? Which is kind of which is because you're kind of going in this direction, right? So you saw that if you slow down.
What was the definition of S dot? Was it the e to the KL, e to the something the KL?
Yeah, S dot is that KL. So S dot is
the KL.
Right. Okay. S dot is this gap between the forward and reverse processes. So the point I was making is that if you had a forward process that was gradual, then the reverse process would also be gradual, and then the gap or the S dot would be small. But if you're extremely aggressive, so let's take the limit of some diffusion process, which in one step converts your data to noise, perfect noise, like the equilibrium state. So in that case, this arrow would be extremely large, right? And the point here is that yes, in principle, the reverse process corresponding to that particular forward process will be able to one-shot reverse you back to the original data distribution, right? But there's a cost to doing that, which is that your network actually will need to remember a lot more information.
But I mean, okay, well, let's unpack it because we don't have a single network. So we have different time points, right? And we have infinitely many time points in any case.
Yes.
So what do you mean by that?
So in the case where the process is extreme, in the extremal case of there being like one time step.
But this is continuous time. There aren't time steps.
Yeah, so you have like one physical network. I mean, physical in the sense of in a computer, right? There's a single unit, right? There's a single unit which is storing all of the accumulated information from all the time steps of your forward process. So S dot is not the information from any single time step. It's the accumulated information. It's like the difference of those trajectories, right? So it's the difference between the entire distribution of the trajectories over the full range of time.
So, but what do you mean that there is only one time step then?
Oh, so when I say it happens in a single time step, what I'm saying is that you basically kind of do this process where, like the noise is turned up so high. So the time scale in the problem is set by the noise, right?
But the time scale is arbitrary.
No, the time scale is set by the noise. So if you have,
but I could slow down. I can reparameterize time as much as I want.
Yeah. What you can reparameterize time, yes. But so, for example, if you take like the VP process or something, right? So assume that you made the noise term large while keeping the drift constant. So then you cannot reparameterize time and get rid of that difference.
Okay, so that's it. That's of course because it's not true in a Brownian motion that I have a single time scale parameter. So the whole process is time invariant. But of course, it is true that, yeah, in variance specific case, you have two time scales essentially. So you need to calibrate them together.
Right. Right.
So you are saying compare with the drift. You're saying that the drift set the scale for the, yeah.
Yeah. I'm saying, you can have diffusion processes in which there is a time scale, right? Because even in the case of the beaker with the ink, there is an inherent time scale because the boundaries, which is the beaker, is kind of acting like an implicit drifter. So even if so this is why I could change the sigma and observe an effect and not just absorb it into a reparameterization of time, because the boundaries don't change in the same way.
It's just that personally, I don't believe that there is a fundamental difference between variance preserving and variance exploding, in the sense that I do think that the phenomenology is largely the same. Of course, the math can be easier or more difficult in one situation of the other, and can be more or less posed in one situation of the other.
But there is a difference. Actually, one of the reviewers in NeurIPS also brought up the same point, and you can actually work out carefully that and find that if you try to make them match, then you find that the variance exploding process corresponds to a variance preserving process with explosive drift or something.
No. I'm not saying that they are mathematically equivalent. I think in some situation you can remap it, but it's not necessarily. I'm just saying that in terms of the phenomenology of what implies to do generative diffusion, I've never seen anything that suggests that there is a fundamental difference or a very good reason for using one over the other. If I'm just thinking about how things are generated, of course, mathematically, often things are very much simpler in one framework or the other, and in practice, things can be computationally more stable in one framework or the other.
I think this is kind of the understated point. So you're kind of hitting. So there is a difference. So there is both a practical difference, which is that variance exploding basically covers a larger region of the data. It explores a larger region of data space. So when you train the model, you basically have to take the Monte Carlo, the approximation of the loss, or a larger ball in space. That is like a practical thing. That has nothing to do with the thermodynamic stuff that I'm discussing, right? The second thing is basically this, which is that, so instead of V process, let's just restrict ourselves to two Ornstein-Uhlenbeck processes, one of which is more rapid than the other. Then you can show very clearly, and I have results in my paper, that if you compare a process which is much more rapid, right, then yes, you can reverse it very quickly, but there's a cost to that rapidity, which is that your network is basically is under more stress because it's storing more.
No, I fully get this point. Like the bit of cognitive dissonance I have is that is it just a quirk of variance preserving?
Or it's not. It's so I would
because
say
this
that
problem will simply not exist in variance exploding, but we know that in practice they're basically equivalent. Because variance exploding is fully time invariant.
Variance exploding is time invariant. Yes, that is correct. If you take some sort of, so the problem is that without the case without drift is actually some sort of special case, and you cannot really compare it to the case with drift. And this is, again, like I said, some measure theory issue. I would think that if you kind of do some sort of at least a mental thought experiment where you think of a tiny drift term, so don't have perfect variance exploding, but you have a very tiny, very weak drift term, and you imagine that is, with the weakness, the variance, by making the drift term very weak, you're converting the variance preserving process to something that looks like a VE. Then you see that the VP process has like a clear advantage. Now, what happens exactly when you take that drift term to perfect zero, that is a little tricky. That I think I can, that's like we should discuss that after.
So maybe a last thing. So there is something tantalizing, right? That is not what you're actually talking about, but there is this tantalizing connection with fast samplers, right? Which again is a different logic that will apply for variance preserving as well. But then at least it seems that the take-home message could be somehow maybe deliver a conjecture for fast samplers, which of course it doesn't apply directly mathematically, but we've been struggling thinking about fast sampling and entropy production for a while. And I just wonder if the same insights will apply in that situation in which you actually, there are time points because you have a finite number of function evaluations.
Yeah, there is a connection. So the one of the processes I consider in my neural entropy paper is this thing called straight line diffusion models. Which is this Ornstein-Uhlenbeck process, which is explicitly designed in such a way that the trajectories are as straight as possible. And the logic is that when you want to generate new samples, you can do as few evaluations of the slope of these lines, right? Because if it's basically a straight line, then you need like the slope at one point, and then you can just slide along the straight line to get the initial samples. Right. And what I show experimentally is that that process actually does have this trade-off where it puts much more strain on the neural network. It forces the neural network to remember a lot more information.
Because essentially, yes.
Because essentially it's kind of like, again, the argument is a little bit more subtle than what I'm presenting here, but essentially the difference is that the purple arrow is much longer for such a process.
So to be clear, when you mean the network remembering more information, because in terms of Shannon, the network needs to, there is a precise amount of information that the network needs to learn in one way or the other, which is the entropy of the source, you know?
That's so the total entropy is not just the difference between the Shannon entropy of PD and the Shannon entropy of the equilibrium distribution. So Shannon entropy of the equilibrium distribution is trivial. Okay, let's throw it away. So you're saying the entropy of the data distribution that's not neural entropy. It is related to it. It is a subset of neural entropy, but it is not the full content of what the neural network learns.
No, I understand, but if you just say information, most people will understand that.
But that would be that would be a little bit of a misconception because the network, given the same PD, different processes require the network to learn different amounts of information to reverse back to PD.
But that depends what you mean by information, right?
It's basically this minus log of the probability of getting that thing naturally. So if you
I just wonder why you call it information.
Yeah, I call it information because it's the negative log of the probability of getting that state. So very simple terms, suppose I give you the ASCII character A, right? Why does it take 8 bits to specify that character? Because it is one of 256 characters, right? And if you assume that all of those characters are equally probable, so there's a uniform distribution over the ASCII dataset, right? Then you say that you need 8 bits to specify it because minus log of the probability of drawing an A is 1 to the power is 8 because the probability is 1 to the power 2 to the 8. Right? So the negative probability of getting that outcome is the information you need to supply to locate that outcome. And in exactly the same way, I'm saying here that if you have some diffusion process, the diffusion process by itself can randomly fluctuate to any other target distribution from its equilibrium distribution. But if you want to locate that consistently every time, you need to specify minus log probability of that happening automatically.
So I am trying to reconcile the way we define information the way you do, because I think now I kind of, I remember this discussion with this Dayan, is that we quantify information in terms of the conditional entropy between the final state x0 and the current state xt, or the initial, but of course we're going in reverse time. So the way we can define information is how much information you need to specify your final destination, but not in terms of distribution, in terms of sample.
Exactly. This is the difference. Yes. So you
Exactly.
need
So
to
we are yeah.
You need to specify it in terms of the distribution, because the generative model is trying to basically remember the entire distribution, right?
Well,
It's
I mean,
not.
that's arguable, right? I mean, that I will disagree. I mean, I think you can have different philosophies because,
No,
in my opinion, fundamental the generative model is generating samples. It's not matching distributions.
no,
So I
no.
see more.
So if it is remembering samples, then it would memorize, right? So it is basically remembering these control values. So the actual neural network is actually storing these what are called optimal control values, which has a one-to-one map with the target distribution.
It is true, of
So,
course.
right.
The network by construction, I mean, it could memorize or not, but let's assume that it's not. Let's assume it is exact. By construction, it will match the distribution. I'm not saying that it will not match the distribution, of course. I'm just saying that it is meaningful to look how much information you're generating about the specific things that you're generating.
But the point is that there is an infinite number of those specific things. So if you have a well-trained diffusion model on images, let's say, it can, in principle, produce infinite variations of your training data, right? So you train it on 1,000 dogs and you get pictures of 20,000 dogs.
No, forget the training data. There is no training data. The model is perfect. It's still in a completely perfect model. Again, we need to translate, because of course you start from a different the assumption that we start often is that, okay, let's assume that we have the perfect model. For example, how do we define?
Still trained on some finite number of
No,
data points.
no, because let's assume that it's perfect. The point that even if you assume that the model is perfect, it's completely targeted distribution, you still have a lot of problems, because you still need, for example, to evaluate your network a finite amount of times. So that's why what we define, what we look at is how much information essentially you get in each function evaluation, even assuming the network to be fully perfect. And in that context, it's quite useful to just look at the information production in the sense of the specific sample that you're generating, which is not a training set sample. It's essentially just what you end up generating, the decision that you make in order to generate what you end up generating.
But now you made an arbitrary decision here, right? So you said that you don't have a finite, your data set is not finite. So you're saying it's perfect in the sense of it has a perfect understanding of the shape of the distribution, but you've chosen to discretize time, right? So what if I just throw away the discretization in time, because the SDE itself is not discrete in time. It's like a
we don't
continuous.
choose to discretize time. We define what the correct or what we define an objective time axis. So we essentially measure time. The fact that, especially in variance exploding, you have no conception of time. So time is completely arbitrary. So what we find is that we define time in terms of information transfer. And that doesn't require any discretization. It's just a definition of time. Then, as an application, it allows you to properly discretize time, for example.
Right, but you need to do that to define whatever notion of information that you're discussing, right?
No, that just depends on so it depends on the target distribution. So if you assume to know the target distribution, you can simply compute. You can derive from the score function. So as far as you assume to have the exact score function, you can derive the conditional entropy rate. In your definition will correspond to the marginal entropy rate. So even if you're actually coming from different point of view, actually your definition give us something that is very similar to what we compute, because your definition in variance exploding give the marginal entropy rate of the distribution.
I guess, let me just kind of try to circle back and, I don't know, kind of conclude this discussion for a little bit, which is the basic point I'm making is that, if you have a finite number of samples and your model learns on this finite number of samples, and it can actually produce more samples than it was trained on, then it is not meaningful to talk about information in terms of information per sample, right? Because you can train a diffusion model on n training data points and generate 10 n data points, and then you keep generating new data points, and you can ask, like, what does it even mean to say that the information in the diffusion model is the information per sample. What I'm saying is you have to think about the information in the neural network as the information associated with modeling the entire distribution, because that is a thing that is invariant to the number of samples that you generate in the future.
Yeah, but it's not what the network is doing. The network is providing the vector field given the current state.
And I'm saying that there's a unique map between that vector field, which is the control, and the target distribution. And this is just standard control theory.
Yeah, but also the information, the conditional entropy rate is a very simple function of the vector field. In fact, it's just a function of its length, of its Euclidean norm.
Yeah.
I'm not saying that what you're doing is wrong. I'm just saying that there are different angles to look at the similar concepts.
And that might be true. So I have to look into your paper and figure out what is the relationship between your definition of information and mine. But all I'm saying is that it's
the
not
formulas
a
are almost the same. So
it's not a
we
per
come
sample
from
thing.
different. Yeah. Well, but ours is not a per sample thing. It's a per time point thing.
Fine.
It's per time point. So you have, but it's not that it's per sample. It's that it's a conditional entropy. So the conditional entropy is not the entropy of the conditional distribution. It's the entropy of the conditional distribution averaged under the data. So that once you do the averaging, then you remove the
once you do the averaging, the sample the individual samples go away.
Yeah, but it still captures the mutual information between the current state and the final state, and those are specific states. They're not distribution. So
when you say state, are you talking about samples or like the actual just property distribution itself?
No. I mean just the specific image or the specific noise corrupted image. So you will have the mutual information.
So when you average it out, the specific sample, the picture of the specific samples go away, right?
Yeah, but the mutual information is still about that. It's the average information transfer between the specific noise. It will give you the average information transfer between the specific noise state and the specific image at time t. So it's averaged, but it's still an average of things that are defined per sample.
Per sample. Okay, so I think the middle ground here is that so what you've done is you've taken what I call neural entropy and taken slices of it. So which is not completely agnostic to the training data, but when I've also averaged over the training data itself, because like I said, I'm kind of talking about information as the information needed to restore the entire distribution. And the entire distribution kind of enters the picture when you do this averaging over all the samples. And, assuming that you have a sufficiently large n and so forth.
So, but how do you analyze it? Because your network is not that analyzing a deep network will be basically impossible, right? If you want to. So
no, you can compute neural entropy, or you can numerically compute neural entropy quite easily.
Okay, you do that numerically, basically just train.
Yeah.
Okay.
Because I don't know the actual distribution is for images. Yeah. There are examples where I take Gaussian mixtures where I know all the answers and I compute neural entropy numerically and with the analytic expressions, and I compare and I see that they match. Yeah. Okay. So I think we're at time. I have some more slides related to the more recent paper. I don't know if you guys want me to keep going or.
Yeah, I mean, for me, it's fine. If of course everyone is free to leave if you have
okay.
Point.
All right. So like I was saying, kind of, the stuff that we like the thermodynamic uncertainty, it's like a standard result in stochastic thermodynamics, even without any connection to diffusion models. And it has this deep kind of connection to Heisenberg uncertainty in quantum mechanics. So here is like an interesting aspect of diffusion models, which is that they've kind of made this like exponential leap over the last couple of years in terms of image quality. And yet there isn't still like a great understanding of why diffusion models are able to get such high fidelity compared to something like LLMs, where you still get things like hallucinations that are quite obvious even when the sample size is fairly small. And I'm not going to claim that I've solved this problem, but I want to kind of show you my 2 cents. So here is a simple experiment from the neural entropy paper. So what I do is I take the CIFAR-10 dataset. I take first 10 samples from each class. So that's a total of 100 training samples because there are 10 classes. And I train a diffusion model on those 100 samples. And as you can expect, that is just too sparse. So the samples you generate kind of just looks like noise. But then I keep adding more samples. So I take a fresh neural network, I train it on 100 samples per class. So that's a total of 1,000 samples. And that gives me something that looks slightly more reasonable. And then I keep repeating this experiment with more and more samples. And I find that, yes, my image quality gets better. But you also see that the image quality between, or the increase in image quality between, let's say, 100 and 1,000 is kind of roughly commensurate with the increase in image quality between 1,000 and 5,000, right? So there is kind of this law of diminishing returns. So it's not increasing linearly. And in fact, if you take measurements of the neural entropy over the number of training samples, you find the following relationship. So this is a semi-log plot. And what this is showing is the information the network captures from when you go from 100 to 1,000 samples is exactly the same information you get if you, or the same amount of information it captures if you go from 1,000 to 10,000 samples. So neural entropy, or the information content of the neural network, grows as log n. Whereas in a conventional memory, you would expect it to be linear in n, right? So if you have 10,000 samples, it would take 10 times as information, 10 times as memory to store compared to 1,000 samples, which is not true for diffusion. So diffusion is this like hyper compression at work. And you kind of see this constantly if you do it for different image data sets. So I have MNIST here, you can try it for ImageNet, all that stuff. But there is a little catch here, which is that if you repeat the same experiment for a situation where the data has very little structure, so something like a Gaussian mixture, and the inductive biases of your network are extremely weak, like MLP, then you see that this trend no longer follows. So there seems to be some sort of dance between the structure of the data and the inductive biases of the network, which when both of these things kind of line up, then you get this nice compressive behavior from a diffusion model. So yes, there's a question.
Quick question. So these are all like trained models. Like,
yes.
Gaussian mixture is trained model. You trained it.
Yes.
It's not.
Yeah. Absolutely. Yeah. This is not like a analytic thing. No.
Okay, I'll ask you then after the talk. Yeah.
Yeah.
I also have a question. In the first row, is basically you train the model using 10 samples?
Yeah, the first row, 10 samples from each class. So 10, dinosaurs, 10 trucks. Yes.
And this is the generation quality you get, or?
Oh, yeah. So I wouldn't say that my diffusion models are, I didn't use it like any guidance or anything like that. So yeah, you can kind of roughly see that this is a truck.
Because I'm saying this because, it is known that when you train, for example, like very few samples, the model will memorize if you push it to have a fully trained model.
Right, exactly. So
I'm just trying to understand what is the kind of like the design of the experiment here.
Right. So I have not trained the model for long enough that it memorized. So all of these models have been trained for like 200 epochs. So yes, you're correct in that, if you have very sparse data set, it will memorize. But there's also research which shows that diffusion models take a long time to memorize. So you have to train for longer and it would memorize, actually, yes.
Okay. Yeah, thanks.
Yeah. So it looks like noise here because I haven't allowed it to run for long enough that it memorized. Thanks. That was a great question. Yeah. Any other questions?
Essentially, you are trying to kind of like measure the amount of information on the condition that you're only increasing the data size access.
Exactly. Yeah, the training data size. Yes.
It's just, I mean, it kind of violates scaling, right? Because that's we do know that training size should be scaled with training time. So do you think that this relationship is meaningful if you're not actually scaling at the same time?
So I'm not scaling time, yes, but I think this graph to me is so it is scaling between information and the number of samples. So of course, no one has actually plotted that before, I think, but it's basically telling me that if you keep pushing more data into the diffusion model, you slow down, right? Which is in the same spirit as the other scaling laws.
Okay.
Like,
This is also.
What do you mean with slowing down?
I find it quite interesting because maybe it's a bit unrelated, but we know that the score gets shorter as you increase the number of training points. The exact score function, the empirical score function, will gradually converge to the exact score of the distribution.
Yes,
but
yes,
also the size of the scores will shrink. Because essentially the more data points you have around and the more kind of there is cancellation in the score is
okay, so it becomes less the score has to concentrate on less. I mean, the probability mass is more distributed, so the score can be
in expectation. So in expectation, it gets smaller. Just the largest value of the score correspond to basically zero information. There is this inverse relationship where the score is very long, there is zero information to be transferred. This sounds a lot like the kind of things you were saying about the work. I think it's really worth for the both of us actually to try to kind of get a bit on the same page in what we are doing, because I do think that a lot of things we are saying actually talk about very similar things, and the formulas are indeed essentially exactly the same. But again, if you look at the conditional entropy, we will say that essentially when the length of the score is maximal, so where the steps, as you're saying, the steps are in average the longest, and that's also true for variance exploding. The information rate in terms of conditional entropy is the lowest. Potentially it's zero. If you have a single one, you have the longest possible score. So as you're saying, kind of you're moving the fastest, and there is no information being produced.
So I think that the statement about very low sample density and the score being very high is related to the fact that, and you can actually kind of see this in the Gaussian mixture case. That's related to the fact that, so if you have, let's say, 10 training samples in total, okay, and you train for a sufficiently long time, then what happens is the diffusion model is just going to think that the probability distribution is a set of delta functions at those 10 points.
Yeah.
Right. Which means it has to really concentrate all the available probability mass around those extremely tiny regions.
Yeah.
Which makes the score function really large around those points.
Yeah.
Whereas if you had like 10,000 points, then the score function can kind of evenly distribute the probability mass. So there aren't these sharp bumps in the probability distribution.
Yeah, exactly. We have studied these things actually quite extensively. The way I like to see it is in terms of destructive interference. When the more data points you, because the score is an average, the score is expected value of the pointing vectors. The score shrinks where there are a lot of data points around you, which causes destructive interference in the average.
That's a good point. Yeah.
Yeah, it's quite a neat interpretation. But it's exactly what you're saying. It's just another way of saying what you're saying. That if the mass is considered in one point, and you have an exponential discounting, so as far as you're close enough to one point compared to the other, then the others don't matter at all. Yeah.
Yeah, that's right. Yeah, the way, I mean, I think this is also related to like the inductive biases of the system, which is that if you're remember how I talked earlier about choosing a prior which restricts you only to smooth candidates of the probability. So you can, if you choose a prior which kind of naturally protects you from overfitting in this delta function kind of way. Or if you choose a prior which, given fewer points, are still able to kind of interpolate between those points very well, then that is, I think, desirable. And I think that's kind of what you're seeing here. So in the MLP case, you clearly see this where when you have like 10 samples, which is this limit, it learns a completely different distribution from what the true distribution is, which is not unexpected, right?
Yeah.
But the magic of like a unit is that it kind of, even in the sparse case, which is, like 1,000 samples in 32 by 32 by 3 dimensional space is extremely sparse. It's still able to kind of not fall into the trap of concentrating everything into a delta function.
Do you have these experiments with vision transformers?
I'm planning to do those.
Because that would be very cool to see. If it's structured, because like, is it inductive bias or is the structure of the images themselves? For me, this is the big question.
I think it's both. So when I say inductive bias, I'm kind of actually talking about, like the symmetries of the network and so forth. So I'm using it as an umbrella term for many different things. But really,
there are two factors, right? There is the symmetry of the network and the symmetry of the data.
And these two things line up when you use a unit, right? I haven't done the VIT case yet. This one does have self-attention layers. And I found that you need the self-attention layers for CIFAR to get even a recognizable image.
Yeah, but the fact of the pure vision transformer is that, at least in its purest form, it does not have any translation on invariance.
This is a quite interesting problem, which is, so let me make the distinction between diffusion transformer and vision transformer. So diffusion transformers actually operate on a latent space constructed from the images, right? So they have these like encoder decoder stages that actually sandwich the transformer phase. So the vision transformer does not have that. The vision transformer is directly patchifying the image and learning to reconstruct the image. But here is an observation about vision transformers, which I've read in papers. I haven't done the experiment to see it myself, which is that if you train a vision transformer for some time, it actually develops convolutional structures within its attention blocks. And so if you kind of go and look inside it, it kind of learns by itself these convolutional filters.
Yeah, but then it means that it's not an attention bias. It's actually reflecting the structure of the data. Or maybe it's a more general bias of just
No, so the way I think about it is, so you know what an FPGA is, right? It's like this piece of hardware on which you can basically write a program to do any chip. So you want to, implement a microcontroller, you can implement any microcontroller on an FPGA. Gabriel. But in the same way, how I think of a transformer, and I have like reasons for doing this, which we will not get into. The transformer is basically FPGA for neural networks in a way. So with the unit, you kind of fix the symmetries of the network, but somehow a transformer is able to learn the optimal network that is well aligned with the symmetries of the data. Whereas with a unit, you choose the symmetries by hand to align with the symmetries of the data. And I think there are some ways of actually demonstrating this, but again, this is like ongoing research. But that's kind of, I think, where the two pictures kind of coincide.
I have a crazy comment that just kind of goes against that, because FPGA is usually more designed, for specific tasks, right? But for transformer, it has been found they have encoded some sort of global representation that you can use for like other different tasks. So, I mean, I'm not saying you're wrong, but it just feels a little bit contradictory.
I would. Okay, so this is basically a loose analogy, right? I'm not saying that the training of a neural network and the programming of an FPGA are like one-to-one.
Yeah.
I'm basically kind of making the point that an FPGA is a more generic substrate on which you can implement many architectures, right? And in the same way, I'm saying that a transformer seems to be some sort of generic substrate on which things like the convolutional structure naturally emerge if you train it in the right way.
Yeah, and
Right.
that seems to be the consensus, right? I think in general, throughout the literature, people have been dropping specific inductive biases, even in molecular generation now, and going for full transformers. And that's, but
Exactly.
I think just seeing the curves that you're showing just for the transformer, for the pure transformer, will be very interesting, and it
Exactly. Yeah, I
can
want to
cast
do
some
this.
light. Yeah.
Yeah, I want to do this, but I get,
And
I'm mostly writing all these papers on my own, so
yeah.
I don't have like when I do one paper, I can only do one paper at a time. So
Also regarding
You should listen, Gabriel.
yeah, also regarding diffusion transformer, another thing to consider if we just kind of ignore the VAE encoder for a second, right? I think in that paper, the guy mentioned he tried a lot of different things regarding time conditioning inside of that model. So that's another thing to consider as well. And I think a recent paper talked about whether you need time conditioning or not. That's also, I mean, it's still quite unclear when the people brings up that you can train these model without time conditioning and it works well. I think it's coming from like Ham and Hay at MIT now.
I see. Yeah, I need to dig deeper into that. I would not say that I'm an expert on diffusion transformers at all. I kind of just, skim the paper. I implemented transformers. I've never actually done any experiments with diffusion transformers.
Yeah,
Um,
it's not
yeah,
too bad. It's just the camp. I think the time conditioning is the main new thing in that model.
yeah,
If you look at it from the compare it to the VIT backbone.
right. So are you saying it's kind of like the positional embedding for regular text, right? So are you talking about like the time embedding in the same way?
Yeah.
Yeah.
Of course there is like positional encoding for the different patches. That will
Yeah.
always be there, right? But the time conditioning is also another thing to kind of pay attention to as well.
That is very delicate. In my experience, it seems that you can do that in many ways, but the success or failure often of a diffusion network depends on the way you do time conditioning. It just since it's so sensitive to this, because since there is this division of labor that at essentially different time points the network does different things. Embedding time correctly really changes performance and lead it from not working to working. I mean, this was quite surprising to me in the beginning, because in the beginning, when I started to diffusion, I felt, okay, but the noise level is implicit in the image, since you can get a very good statistical estimate just from the image itself of what the noise level is. It turned out that you need a level of precision that really need to be correctly encoded in the network. Close to zero, essentially. Essentially, the truth is, for a high noise level is fine. But if at least if you want to generate images, you need to be very careful to what you do very close to zero. And then that's where the crucial, the importance of the time embedding really comes.
This is, sorry, I didn't want to interrupt.
I just wanted to say, I think what Bao was thinking was a recent paper that showed that you don't need time, right? Is that the...
Yeah, but I think even in that paper, they show they do better than the regular post, but it's not really the state of the art as well. So, but they do show that it works.
I mean, we did try also with Gabriel. I mean, in general, without time, yes, it works, but not as well. So I mean, so yeah, of course it does work because you can kind of read off time from the noisy state. But in our experience, it doesn't work as well. And maybe they again, we should read that paper to see if they discover something new, and maybe transformers are more able to detect the time that. But I would be surprised if that it works better in general. That's from what I know now.
Could you share the paper, Ivan?
But maybe just that we're going a bit in a tangent.
Oh yeah.
Let me kind of maybe quickly go. So by the way, you should also read my new paper, which is what I'm going to talk about next. Although I don't address this particular issue in the slides, I do talk about how there are actually some singularities at early time which are not the singularities you usually think about because the sigma s is going to 0 or something, or sigma t is going to 0. There is like another genuine information theoretic singularity there. because of the manifold hypothesis. So when you go from like a higher dimensional data Gaussian ball and you try to converge on a lower dimensional data distribution, the amount of information you need to inject at the final time steps blows up.
Yeah, we had actually several papers on this subject. Like,
Okay.
Like we have like our recent spectral gaps paper, for example. I mean, that wasn't specifically about what we studied are the eigenvalues of the Hessian matrix of the Jacobian matrix. You can prove that those eigenvalues are actually, if you look at my latest preprint, it's still a bit drafty, but the information dynamics, you can look at the eigenvalues of the Hessian are essentially determinate the information production in terms of conditional entropy, and even in terms of marginal entropy. So that's probably what you're saying, right? Essentially, where you have this orthogonal derange that creates this kind of infinite divergence.
Yeah, there is. This is also, again, I come from it from like a measure theory perspective, but yeah, you can show that. Yeah, it blows up. Again, I probably won't have time to discuss it, but I can go and do the rest of the talk if we have, I don't know, another 10-15 minutes, but
I mean, it's fine for me.
Okay, so all right, so we're here, but I want to kind of take like a little bit of I want to switch in a slightly different direction because so as I said, these graphs seem to suggest that diffusion models are extremely good at compressing images or whatever data they're given. But there is this super intimate relationship between compression and gambling. And this is something that actually I wasn't aware of. But let me kind of tell you what the connection is. So suppose you had the following simple game. So you have a dice under a cup, and there is a dealer who basically shakes the cup and asks you to place a bet on what the die is going to throw. So the dealer believes that this is a perfectly fair die, and therefore they offer you a 6-to-1 odds. And what that means is if you place $1 and if you win, then you get $6. Okay. And this is called fair odds because if you place a bet on each of the possible outcomes, you end up spending $6, and one of those outcomes will appear, and you gain $6, so you break even. And this is what's called fair odds. But suppose you knew that the die is actually not a fair die, and in fact, it actually has some sort of bias towards, let's say, the values 3 and 4. Okay, and you knew this somehow, the dealer doesn't. Given the situation, what is the amount of money you can make over n throws, assuming that n is sufficiently large? Okay, so this is like a standard problem that you would, I don't know, encounter in like a quantitative trading interview or something. And to answer this, we're going to do some simple-minded version of a Monte Carlo simulation. So okay, so what I'm going to do here is I'm going to throw 36 dice in this experiment, which is equivalent to throwing one die 36 times, right? So my n is 36 here. And I'm going to show you the sum of these outcomes on the right-hand side. So you see that, the outcomes kind of, as I go through different outcomes, the arrow is kind of building up a histogram of the sum, right? I'm using the sum as a proxy to kind of represent the, state on the left with one real number. So I'm going to speed this up. I'm going to throw very fast. So I do like, some 100,000 rolls of the same 36 dice. And I find that the sum is distributed in this specific way, right? And this simulation was done with the true die distribution. So I used the blue curve here to represent the true distribution that we know. Now, if the dealer had done exactly the same simulation, they would find the following distribution. So you see that he assigned some probabilities to some states, which we don't, right? Or in other words, the states that we predict will happen are a lot more concentrated than the states that he predicts will happen. And this is where we have an edge, right? So we can place our bets only on the fewer number of states that we know are more probable than the one compared to the one that the dealer thinks is probable. And if you take a larger value of n, then this difference becomes even more pronounced. So what I've just shown you is just an example of the asymptotic equipartition principle, which is that there's a subset of typical sequences amongst all possible outcomes, which are going to be the most probable, and they will all have roughly the same probability if n is sufficiently large, right? And there are 2 to the power n hx of these typical, or that's the cardinality of the typical set, where hx is the Shannon entropy. Now, the strategy here is you take your initial capital, let's say $1,000 or something, and you distribute it evenly over all the typical sequences. So this is exactly equivalent to, taking whatever money you have and iteratively placing the bets on the individual games one at a time. So what you're doing instead is you're taking the ensemble of all possible sequences which are possible, and then placing bets across all of them. And since you're placing bets only on the typical sequences, one of these is going to win, right? And it's going to win with a probability 1 over 2 to the power hx. And you placed V0 over that number of dollars in that bet. And that bet multiplies by 6 to the power n, because that is the sequence which will win at every turn.
So just how do you know in advance that the sequence is typical or not?
Well, I know what this is, right? And all the throws are independent.
No,
so
but
if I know
but when you place a bet, you need to do time by time, right? Now you're saying that you're placing a bet on the whole sequence.
Yeah, that's because these are independent events. And so, yeah, you can convince yourself that the doing it sequence by sequence or one at a time is the same as placing the bet on the entire sequence. It may not be immediately obvious, but it's exactly the same
So,
thing.
but you're saying that you're betting 0 on non-typical sequences and you're betting some finite sum on typical sequences.
Exactly.
But that's, you cannot, at the first throw, you cannot know if something is typical or non-typical. So
no, I'm actually counting it across all throws. So if I'm allowed n throws,
oh, okay.
I am, yeah. So assume that
you're doing
I know what the initial state is for like all the typical sequences, right? So I kind of assume that all the throws kind of happen in parallel or something like that.
At the same time, okay. You're not doing sequentially. Okay.
Yeah. So you can show that if you do the other thing of like placing the bet one at a time, it's exactly equivalent.
Okay, you get it. All right.
Yeah, it's okay. But anyway, so the point is that if you do this exercise, then you find that your doubling rate, which is defined in this way, so this is basically a measure of your gains, is going to be log 6 minus hx, right? Which means that if you so the dealer assumed that the distribution was uniform, which is where the log 6 essentially comes from. And we actually knew the true distribution, which is why we have the access to hx. And so the point here is that if you had a low entropy game, so in the extreme limit that this die only produced one outcome, right? hx would be as small as possible, which means that our return would be as high as possible. So low entropy games produce higher returns. All right. So now this brings us to the idea of mutual information, which is I'm going to modify the game by introducing some sort of communication channel. which if the communication channel were perfect, it would basically tell me exactly the outcome inside the cup before the dealer even opened the cup. So in this case, I win every time, right? Because there is no more uncertainty in the problem. So it's like setting hx equals 0. But suppose that there is some noise in the system, right? So the first scenario is the no noise case, and you learn perfect information about X. And the second scenario is where you have some noise in the system, which means that if you know Y, you don't know X perfectly, but you have some better idea of what X is compared to not knowing Y at all. In other words, the Hx, which is the entropy of this orange curve, gets replaced by the entropy, the conditional entropy, given the measurement, right? So on average, these curves are narrower than the marginal, and therefore you have some information edge. And therefore, all you need to do to find the new doubling rate is to replace for the doubling rate with y, the hx with hx given y. And therefore, this communication channel increases your doubling rate by this number, which is nothing but the mutual information, right? So mutual information is kind of almost antithetical to entropy, which is that if entropy is the measure of uncertainty, mutual information is kind of the reduction in uncertainty. And of course, there are many equivalent formulas for the mutual information. This is another formula, so it's the KL between the joint and marginal product. All right, so all the stuff is this is called the Kelly criterion, by the way, what I just discussed, and this is Kelly's paper. The statement from Kelly's paper is that we can interpret this additional doubling rate as, basically the due to mutual information established between Y and X due to the communication channel. So what's the point of discussing this? Well, in a diffusion model, I told you that you have this between these different pixels, you can imagine that there is some sort of like correlation between these pixels. And I also told you that, if you look at the expression for the total entropy, it can be written in terms of the marginals, right, in the entropy matching case. And so if you play with that expression a little bit, so if I explicitly state all the, so x1 up to xd are the different components of, for example, an image, right? So it's the components of the x vector. Then you can kind of factorize the neural entropy into two pieces. So one is this piece which actually looks a lot like the mutual information, except it's like a higher dimensional generalization of mutual information called total correlation. And the other piece is like a trivial piece, which kind of tells you about the difference between the marginal of each component in the data distribution and the marginal in the equilibrium distribution.
Okay, wait. So wait, can you recap? So, okay, the equilibrium distribution and PD.
So the equilibrium distribution factorizes because it's just a Gaussian, and so you can split. And what I'm saying is the data distribution does not factor.
So this KL is the entropy of PD.
The scale is the entropy. Well, no, the scale is not the entropy. It's the neural entropy. So it is.
Yeah, but it's.
So the entropy.
But it's also the entropy of PD minus the cross entropy, right? By definition of KL.
Right. Yeah, so it has both of those components, yes.
Yeah, okay. So you're saying that this is related, and this is some.
This has the same structure as the mutual information. So this first term in the green box here is essentially capturing the correlations between all the pixels.
Yeah,
right? Because the second thing doesn't have anything about correlation. That's why it kind of factorized into the sum for each pixel separately.
Yeah. And so the second term will be?
So the second term is just, it's evaluated at each pixel independently. So this is just going to come from
yeah. It's like the marginal kind of
it's a marginal at each pixel.
The marginal scale. Okay, this is super interesting because we are studying these things a lot in the concept of fast sampling. Sorry, and indeed it just kind of this give a connection between the kind of the entropy rate, the information rate,
right,
and the correlation between pixels.
Right.
Yeah. This is something we discuss a bit, Ian, right? It's very nice that we see this also in this paper as well. Okay, but just go on. But this is super exciting for us.
Yeah, right. So the point is, there's generalization of mutual information that appears naturally in the definition of neural entropy, right? It's a component of neural entropy. So the story here is that when you do the reverse process, you're basically re-establishing all the correlations that were erased by the forward diffusion process.
Yeah.
Right. And you do this in this tricky way where even for the samples that were not in your training data set, you're able to kind of discover those samples by re-establishing these correlations. But so yeah, the point is the total correlation is not just between two random vectors, it's between like a large number of those. And that means if you look at something like, Inpainting, it's essentially doing this, placing a bunch of Kelly bets. It's betting on the value of the unknown pixels based on the known pixels, right? So this is one of the themes of the paper. And of course, I kind of animated it in this autoregressive way, but you know that it's not autoregressive. It kind of makes all the bets simultaneously. And this is one aspect of the new paper that I think I shared with Dijon. So, which is that I talk about the connection between this and the manifold hypothesis and so forth. But essentially, the statement here is that whenever a diffusion model generates an image, it's placing a Kelly bet. And of course, the paper goes into much greater detail about the equivalence between these two situations.
So do you have an application for this?
So this is I wouldn't say an application. I would say it basically explains many aspects of diffusion models. So first, it explains how classifier-free guidance works, what are its limitations. And I point out that the reason you need something like CFG is because the innate mutual information between the labels and images in typical image datasets is very low. So again, this is an aspect that's not fully captured in these slides. But actually, let me just do the following.
I mean, sometimes it's high. It depends on in prompted diffusion can be high.
Sorry, what was that statement?
In prompted diffusion, like in the mutual information could actually be quite high because some prompts are close to be memorized.
What is prompt-based diffusion?
With linguistic prompt, right? I mean, if you look at classes like ImageNet, it's very low. But if you actually look at prompted diffusion, maybe it's low on average, but there are situations in which if there are classes in which they're almost.
It varies from class to class. That I don't disagree with. All I'm saying is that there is. So you have like an extremely high dimensional vector, which is your image, and then you have this other random variable, which is this extremely low dimensional thing, right? And this kind of creates this like dissonance between how well they can be correlated. So there is. Let me show you like one quick thing, and I think I'll stop with that. Okay, can you see the paper? So
yes.
All right. So in this paper, and I haven't discussed this in the slides, but there is this equivalent expression. So I show that if you have a conditional diffusion model that generates images. So Y is the label here and X is the image. So if you have a conditional diffusion model that generates images based on some condition, And if you compare it to an unconditional diffusion model trained on the same image set, but without being shown the labels, the difference in information stored between those two diffusion models is exactly the mutual information. Or in other words, the conditional model has to remember an additional amount of information, which is exactly the mutual information between X and Y.